Okay, let's just start with this. The world around you right now, all of it, the sounds you hear, the voices, music, it's all just invisible energy.
It's completely invisible. And every single one of those sounds, it starts as a tiny, rapid movement, a vibration.
So today we're going to get into the science of that, how these tiny movements in the air become, well, everything from a whisper to a jet engine.
And there's one really important rule we have to start with. Sound needs something to travel through. It needs a medium.
Right. It's why in science fiction movies, a big spaceship explosion in outer space should actually be completely silent.
Exactly. Space is a vacuum. There are no molecules for the sound energy to bump into and pass along.
But here on Earth, it uses air or water or even steel.
Yep, anything with molecules will work. But if you have no molecules, you get no sound, just silence.
And this energy is moving seriously fast. Through the air, it's traveling at about 767 miles per hour.
Which is why you always see the fireworks before you hear the bang. It's a rapid energy transfer, not some slow, lazy wave.
Okay, so let's get right down to the source. The vibration itself. What is actually happening?
Imagine a guitar string. When you pluck it, it starts moving back and forth, right? Oscillating around that central point.
It moves so fast, it just looks like a blur.
That blur is the engine of the sound. So as the string swings forward, it physically pushes the air molecules next to it, squeezing them together.
Ah, creating a little patch of high-pressure air.
A very temporary one.
Yeah.
Because then the string immediately snaps back.
And when it snaps back, it leaves a kind of gap, pulling the molecules apart.
Right, which creates a zone of low pressure. And these two actions are the absolute building blocks of every sound wave.
Do they have technical names for those?
They do. The part where the molecules are squeezed together, the high pressure zone, is called a compression.
Okay.
And the low pressure area where they're spread apart, that's called a rarefaction.
Compression and rarefaction. So sound isn't like ripples on a pond where the water moves up and down.
That's a perfect way to put it. It's a totally different type of wave. Sound waves are longitudinal waves.
Okay, what does that mean, longitudinal?
It means the air molecules themselves are moving back and forth in the exact same direction that the energy is traveling.
Oh, I see. So the energy moves across the room, but the air particles are just sort of shuffling back and forth in place.
Precisely. Think of a long metal spring. If you push one end, you see a wave of compression travel all the way down it. The coils themselves don't fly across the room, they just nudge their neighbor.
It's a chain reaction of tiny pushes and pulls.
Exactly. And if we want to measure that wave, we can start with its physical size. We call that the wavelength.
And the wavelength is just the distance from one of those squeezed together parts, the compression, to the very next one.
Yep. The distance between one compression and the next. But maybe even more important than its size is its speed.
You mean how many of those waves pass by in a certain amount of time?
Exactly. And that brings us to our first key measurement, frequency.
Frequency is just how many vibrations or cycles happen in 1 second.
And we measure that in a unit called Hertz. So 1 Hertz, or Hertz, means 1 complete cycle 1 push and pull per second.
And that number, the frequency, is what determines the kind of sound we hear.
Totally. A slow vibration, say 100 times per second, gives you a low frequency, a really deep, rumbling sound.
But if something vibrates thousands of times per second, like 15,000 hertz.
And then you get a high frequency, a very shrill, piercing sound.
And this is what we call pitch, right? Pitch is just our perception of that frequency.
It is. They're directly linked. High frequency equals high pitch, like a whistle. Low frequency equals low pitch, like a big bass drum.
It seems like the size of the object making the sound often has a lot to do with it.
It's a great predictor. A huge instrument like a tuba moves a lot of air slowly, creating a low pitch. A tiny piccolo vibrates air very fast, making a super high pitch.
So what's the range for human hearing?
Our ears are amazing. We can typically hear from about 20 hertz.
Pitch is so low, it's more like a feeling, like a rumble in your chest.
Right, all the way up to around 20,000 hertz. But that high end is often the first thing to fade as we get older.
Yeah, you start to lose those really high frequencies.
It can even start in your late teens. You lose the ability to clearly hear those high-frequency sounds in speech, like an S or an F, especially if there's background noise.
Meanwhile, your dog is living in a totally different sound world.
Oh, completely.
Yeah.
They can hear frequencies way above 20,000 hertz. It's why a dog whistle is silent to us, but, crystal clear to them. They're hearing things we literally can't perceive.
Okay, so frequency determines pitch, how fast the wave vibrates. What about volume? How loud or soft a sound is?
That is determined by the wave's amplitude.
Amplitude.
Amplitude is simply a measure of how much energy the wave is carrying.
So if you pluck that guitar string really gently, It barely moves. That's low amplitude.
Low amplitude, low energy, a quiet sound. But if you really strum it hard, it swings wide, pushing the air with much more force.
That's high amplitude.
High amplitude, a lot of energy hits your ear, and your brain says, that's a loud noise.
It's why you can physically feel the bass from a huge speaker at a concert. You're feeling the massive amplitude of those waves.
And we have a unit to measure that loudness. We use decibels, or dB.
So a quiet whisper might be what, around 30 decibels?
About that, yeah. And a normal conversation is around 60 dB.
But the scale is a little tricky, isn't it? It's not a straight line.
It's not. It's logarithmic. An increase of just 10 decibels means the sound is actually 10 times more intense.
Wow. So a rock concert at 110 dBs isn't just a little bit louder than a conversation. It's thousands of times more powerful.
Exactly. When you turn up the TV volume, you're not changing the pitch. You're just cranking up the amplitude of the waves coming out of the speaker.
So we've talked about sound in air, but it can travel through pretty much anything with molecules.
Right. And here's something that might seem a bit counterintuitive. Sound travels much, much faster through solids than it does through air.
Why is that?
It's all about density. In something like steel, the molecules are packed super tightly together. So when one vibrates, it immediately bumps into the next. The energy transfer is incredibly efficient.
So in air, the molecules are more spread out, and it takes more time for the vibration to jump from one to the next.
A lot more time. It's also very fast in water, around 4,800 feet per second.
Which explains how whales and dolphins can communicate over such huge distances in the ocean.
Hundreds of miles in some cases. The sound just travels so efficiently.
And even in the air, the speed isn't fixed. It changes with the temperature.
It does. Warmer air means the molecules are already moving around faster, so they pass the sound energy along more quickly.
So what happens when an object, like a jet, travels faster than the sound it's creating?
We call the speed of sound Mach 1. When a jet breaks that barrier, it's literally outrunning its own pressure waves.
And all those waves get compressed together behind
They
them.
do. It creates a massive shock wave, like an invisible wake in the air. We call that a sonic boom.
And that's the huge explosion sound you hear on the ground.
That's the sound of that compressed wave hitting you all at once. You can be strong enough to rattle windows.
We see that speed difference all the time in a thunderstorm. You see the lightning flash instantly.
Because light is incredibly fast. But the sound, the thunder, is much slower. You have to wait for that wave to actually reach you.
Okay, so we know how sound is made and how it travels.
Yeah.
How do our ears turn all this invisible energy into something we understand?
Our ears are just phenomenal converters. It all starts with the outer ear.
The part we can see.
Right, it's shaped like a funnel to catch those sound waves and guide them down the ear canal.
And at the end of that canal is the eardrum.
A thin piece of skin that vibrates when the sound waves hit it. It perfectly mimics the frequency and amplitude of the original sound.
And then that vibration gets passed on.
It gets amplified by the three smallest bones in the human body. The hammer, anvil, and stirrup. They act like tiny levers.
From there, it goes into the inner ear, into that snail-shaped thing, the cochlea.
The cochlea. It's filled with liquid, and inside are thousands of microscopic hairs. This is where the real magic happens.
So the vibrations make the liquid and the hairs move?
Exactly. And different pitches make different hairs vibrate. When they move, they create electrical signals.
And those signals go straight to the brain.
Straight up the auditory nerve. The brain gets this pattern of electrical pulses and instantly decodes it. Tells you if you heard a car horn or a friend's voice.
That is just an incredible process. Now, since sound travels in waves, it can also bounce off things.
Right, which is what an echo is. The sound wave hits a hard, flat surface, like a canyon wall, and reflects right back to you.
This is why recording studios have all that soft foam and carpet.
Exactly. Soft materials absorb the sound energy. They stop it from reflecting and creating those distracting echoes.
And we use this idea of reflection in technology all the time, like sonar on a ship.
Sonar is a perfect example. A ship sends out a sound pulse, a ping, and then it listens for the echo.
And by timing how long it takes for the echo to come back, they can figure out how far away something is.
Whether it's the ocean floor or another submarine, bats do the same thing.
Echolocation.
Right. They send out these high-frequency clicks and build a 3D map of their surroundings just from their returning echoes. It's how they hunt in total darkness.
Hospitals use it too, with ultrasound.
Yep. High-frequency sound waves that bounce off internal organs to create an image, all without any harm to the body.
So we've gotten pretty good at capturing sound, too. I mean, from old vinyl records to digital files.
It's all just another form of conversion. A microphone basically works like your eardrum. It has a thin membrane that vibrates with the sound,
And it turns that physical vibration into an electrical signal.
which is then converted into a digital code, a string of numbers. That code can be stored, copied, sent anywhere in the world.
And then a speaker just reverses the process. It turns the numbers back into an electrical signal that moves a cone to recreate the sound wave.
But that ease of use, that digital power, has led to a really serious issue, and that's protecting our hearing.
This is so important because most hearing loss is permanent.
It is, and it all comes back to those tiny, delicate hairs inside your cochlea.
So loud noises make them vibrate too much.
Way too much. They're forced to move so violently that they can bend, break, or just die.
And once they're gone, they don't grow back.
They do not grow back. The damage adds up over time, and it's irreversible.
And the level that causes damage is probably lower than most people think.
Much lower. Long-term exposure to anything over 85 decibels, which is about the noise level of heavy city traffic, can cause permanent damage.
Wow. And what about headphones?
That's the real danger today. Listening to music with earbuds at, say, 3/4 volume can easily hit 100 decibels. At that level, you can have irreversible damage in just a few minutes.
So what's the solution? How do we protect ourselves?
Rule number 1 is simple. Keep the volume down on your headphones. A good rule of thumb is if you can still hear someone talking to you at a normal volume, you're probably in a safe range.
And what about loud environments, like a concert or using power tools?
Wear earplugs. It's that simple. They are designed to reduce the amplitude of the waves before they even get to your eardrum.
They just lower the energy level.
They do. And one more thing. Just give your ears a break. Spend time in quiet places. Let them rest and recover, especially after you've been somewhere loud.
So when you pull it all together, the world is just humming with this invisible energy, these structured waves of pressure.
There's a complex science, but it's happening all around us, all the time. And it's processed by this incredible, but very fragile system inside our ears.
The science is fascinating, but the message is pretty clear.
It is. Now that you understand how it all works, you have the power to protect that amazing system. So make sure you can enjoy all the sounds the world has to offer for a very, very long time. See you next time.